So what we're talking about now is stresses and beams. And the stress tensor is equal to the stress due to tension or compression, plus the stress due to bending moment, plus the stress due to shear force, plus the stress due to torque. And so we're just going to go through these one by one. The first one is tension compression. We've already done this calculation, but I'll just do that first. So the first category is stress due to tension and compression. So for example, let's say that we have this beam and we've already calculated the external loads. So let's say that there's 8,000 newtons that way on the left. And then at the center, there's 2,000 newtons to the right. And then at the right, there's 6,000 newtons to the right. And let's say that the cross-sectional area of the beam is 1/1000th of a meter squared, so 0.001 meters squared. And we want to calculate the stress due to tension at this location. So we want to calculate the stress tensor due to tension along that dotted line. And our coordinate system, this is the coordinate system we always use for internal loads, has the x-axis pointing to the right along the long axis of the beam, and the y-axis up, and then the z-axis would be coming towards us. Notice that what looks like a dotted line in that picture is really an area, in 3 dimensions. And the stress on that area, so if the thing has a rectangular cross-section this way, if you turn it towards you, you see a rectangle. And the stress is going to be the same everywhere on that surface. The x normal stress, so sigma xx, is just going to be equal to the tension divided by the cross-sectional area. We use this same formula when we were doing the stresses in like truss members. And so the first thing we have to do is calculate the tension at this point. You could probably just think your way through it, but let's do the cut at that dotted line and calculate what that internal tension is. So for the cut, I'm skipping all this stuff. So we're ignoring this 6,000 Newton force. Over here we have 8,000 newtons. And then here we have 2,000 newtons going this way. And then we have an internal tension there that's applied by the part we're skipping. I'm going to ignore, well, is that all there is on this? All there is tensions on this, so that's everything. So if we calculate, if I put the shear force, the bending moment, the torque, there's none of that going on anywhere else, so those would all just come out to be 0. And so Newton's second law says negative 8,000, 0, plus positive 2,000, 0, plus T0 is equal to 0, 0. And so T is equal to positive 6,000. So along that surface where I made that cut, is that in tension or compression? That's in tension. And now that we have that internal tension, the X normal stress is equal to the tension divided by the cross-sectional area, which is 0.001. And so that is 6.0 times 10 to the 6th pascals. And notice that the sign of that stress element comes from the sign of the internal load. So you can just trust the sign you get from that formula. Okay, so then if to put that in a stress tensor, the stress tensor would be 6.0 times 10 to the 6, 0, 0, zeros everywhere else. Pascals. What's the principal stress tensor? This is the principal stress tensor because there's no shear stresses. And then if you found the coordinate system where the maximum shear stress occurred, what would the maximum shear stress be? Yep, so it would be at a 45-degree angle about y or z, and you just get a value of max principal stress minus min principal stress divided by 2, so half of this. So 6.0 times 10 to the 6 minus 0 divided by 2. So the maximum shear stress at this point would be 3.0 times 10 to the 6 pascals.
So the principal stress is
Yes. The eigenvectors tell you the orientation of the coordinate system, but usually we don't really care about that. Mm-hmm. Yeah, if all you want is that value, then you can do that. If you also want, if you want to know what that entire stress tensor looks like in that coordinate system, then you have to do the rotation matrix. Any questions about that example? If you want to find, so if you wanted to find a stress tensor where the entire stress tensor where this is one of the shear stresses, then you'd have to rotate this, well, rotate the coordinate system 45 degrees about either the y or z axis. Yeah. But for most practical purposes, all that you want is that value, the maximum shear stress, and that you can get with just that simple formula. Okay, well, that's about it for calculating the stress due to tension and compression. So the next one is the stress due to the bending moment. And so I'm going to give you a formula for this and for each of them. And the formula comes from making simplifications for the problem that are justified for some reason, you know, like either by things that people have noticed from measurements or from making geometrical simplifications to the problem. And so for this one, I want to start by telling you what the limitations are for this formula. So when is the approach that we're using for bending moments applicable? And so here is the list. So these are, I'm going to start with requirements for the beam. The first one is the beam has to be straight or nearly straight. The closer it is to straight, the better the approximation is. And I'm going to list out, I'm going to just do little pictures of what we can calculate and what it would look like in cases where we can't do the calculation. So first of all, when I talk about straight, I'm talking about the long axis of the beam. So we can do that, but we can't use this approach for something like that. So if you have a really sharply bent, slender member, you can't use the formula that I'm giving you here. And assumption is that it's prismatic. So if we're looking along, like down the long axis of the beam, that's what a prismatic beam looks like. What we couldn't do is something like, so say we have something like that, where as you go along the beam, the cross-sectional shape changes, or the cross-sectional side length change. So we can do these, we can't do those. And then, yes. Yes. Mm-hmm. As long as it stays circular. Yep. And the third requirement, so this is the one that tells you we can do this with a lot weirder shapes than just rectangles and circles. The only other limitation on the shape is that the cross section is symmetric about the y-axis. Okay, so think for a second about the coordinate system we're using. Let me go back up to this picture. So we're always going to be using a coordinate system with the x-axis along the long axis of the beam. The y-axis is up, and the z-axis, the way I have it drawn there, is out towards us. Okay, so if you look from this end on the beam, the x-axis would be coming towards us, the y-axis would be up, and the z-axis would be to the left. Okay. So we can do shapes like this. Okay, because this is symmetric about the y-axis. The z-axis would be this way. We can. But we can't do shapes like this. Because this one is symmetric about a horizontal axis. But not symmetric about the y-axis. Yep. Okay, so yeah, so the real problem isn't how you orient the coordinate system. The real problem is how the symmetry relates to the bending axis. So the key here is that it's symmetric about y, and our bending axis is z. Okay. In this case, our bending axis is, so, you know, if you flipped it so the y-axis was that way, and then you're like, yes. But the problem is that if you're still bending the beam down this way, you haven't changed the relationship to the bending axis.
Is the Z supposed to be coming out of the page?
No, so what we're doing is looking at the cross section. We're looking like from the end of the beam down, and so, you know, this is a long beam that has this cross-sectional shape into the page. So the x-axis would be pointing out at us. Okay, and now there's a couple of mathematical preliminaries I have to introduce before I give you the formula. You do well in these, you make it to the mathematical finals.
What?
That just occurred to me because of the Olympics. Yeah. Yeah. Okay, so there are two things that I need to introduce here. The first is the neutral axis. That one's easy. And the second one is the area moment of inertia. That one's not that hard, but it's going to take more time to do that than to find the neutral axis. So area moment of inertia. And this is the thing that people are taking dynamics. This is the one I said to be careful about. This is I sub A. The mathematical definition is similar. It has a parallel axis theorem. It's all blah, blah, blah. But it's different than the moment of inertia that we use in dynamics. That's the mass moment of inertia. Okay, so first, the neutral axis. In the beam's cross section, the neutral axis is a horizontal line passing through the cross-section centroid. So if this is the cross-section, and we're talking about beams, so this is a long, slender thing, but that's the cross-section. The long part is going into the page. The centroid is here. And so the neutral axis is this. And we're always going to position our coordinate system with the origin lying along the neutral axis. So that's always going to be our y. This is always going to be our z. So the origin always lies on the neutral axis. Notice that in 3D, am I going to try to draw this? Okay, so in 3D, there's the beam. Okay. The neutral axis looks like this. Cross section. It goes straight across through the centroid of the cross section. And wherever you take a cross section, that neutral axis exists. So you could really think of the neutral axis as a surface, if you like. You may. And I bring that up because when I introduce the formula, we're going to have to picture the neutral axis in like from that side view instead of from the cross-section view. So notice the neutral axis is really surface. And so that surface, if you're looking, you can think of that as a line across the cross section. And it also makes a line across the side or whatever you call that. Line in the side view. And the coordinate system then would be the y-axis like that, the z-axis like that, the x-axis like that. Okay. So we would do the problem in the xy plane. Do the internal load problem in the xy plane, and then the restrictions on the cross-sectional shape would be in the yz plane. Okay, so that's the neutral axis. And now that we've defined that, we have to define the area moment of inertia. And this measures how well the cross-sectional geometry resists bending. So something that is designed to bend very little when you apply big bending moments to it, like an I-beam, that's the benefit of an I-beam, would have a big value of the area moment of inertia. And something that's not designed to stay undeformed with big bending moments would have a low area moment of inertia. An example would be like, so a rubber band is flexible mostly because it's rubber. This is just a geometry thing. So, yeah, but here's the most extreme example. So this thing doesn't have very much area, but because of the shape, it's really good at resisting bending. Like I can't bend it down, you know? If I try to bend it, all it does is fold in the direction I'm not looking at. But this way, it can't resist bending at all. And so there's something about the fact that if I'm trying to bend this end down, this cross section spreads material out a long way in the plane that I'm trying to bend. Okay, you see what I'm talking about? And this way, the material is all really close together in the plane that I'm trying to bend it, and so it can't sustain any bending moment at all. Okay, so that's going to be the idea of the area moment of inertia, how much we spread the material out from, like, if you're in the plane of the bending. And that's sort of the same idea as that mass moment of inertia that resists rotation that we talk about in dynamics, but they do different things. So first of all, notice this is not the same thing as the mass moment of inertia in dynamics. Even though people call them both moment of inertia, and people denote them both I sub A, and they both have a parallel axis theorem. So that's three things trying to convince you that these are the same thing. They're not. The definition of the area moment of inertia is an integral definition. So the moment of inertia about an axis is equal to the integral over the whole cross-sectional area of I squared dA where y is the distance from the neutral axis to the infinitesimal area dA. We are going to do this for a couple of common shapes. Let's see. So, well, let's do this. Let's use this integral formula and derive the area moment of inertia for a rectangular shape. So we'll derive I sub A for a rectangular cross section. Okay, so here's the rectangle. The neutral axis goes through the centroid, so that's the neutral axis. We'll call the base W, and this is the height, H. And we'll break it up into little strips like this. Where Y, the distance from the neutral axis to the strip, is this. And the thickness of the strip is dy. Then what's the area of that strip? Yeah, dA is, well, let's see, no, W dy. dA is W dy. And so the moment of inertia about the neutral axis is equal to the integral from a y value of negative h over 2 to positive h over 2 of y squared times dA, which is w dy. And so that's equal to, I can pull the w out, w times the integral from negative h over 2 to positive h over 2 of y squared dy. And so that's equal to w times y cubed over 3, evaluated from negative h over 2 to positive h over 2. And that is w times, we have h cubed over 24 minus negative h cubed over 24. And so we get w h cubed over 12. Okay, so just like in dynamics and a lot of times with stuff like this, these integral formulas, I'm just going to give you formulas, simple formulas that come from the integral definition, and we're just going to use the simple formulas. So the moment of inertia for two common shapes. The first is a rectangle. And so if this is W and this is H, and your coordinate system is like this, then the area moment of inertia about the neutral axis is WH cubed over 12. And then for a circular cross section, these are common cross sectional shapes. So a circular cross section if the radius is r, so there's the coordinate system. The area moment of inertia about the neutral axis is I r to the fourth over 4.
So I was wondering if there's a reason why it's not just called I differentiate between the two. Like,
Yeah.
if it's IA, why is that I?
Okay. So the idea of I guess that sort of has to do with the next thing that I'm going to talk about. But there's a sum formula. So if you have, it wouldn't be super helpful if the only things that we could calculate the area moment of inertia for were rectangles and circles. But these end up being really useful because there's a sum formula that says if we have a complicated shape that's all made out of rectangles and circles, or you can approximate it with these, there's a way to combine them into a total area moment of inertia. But the total area moment of inertia has its neutral axis somewhere different than the individual ones. So these are the area moment of inertia for the neutral axis of the individual shapes. That's not necessarily how we're going to, so we're going to have to use the parallel axis theorem to get the area moment of inertia for, like, for example, for this about the total shape's neutral axis, which might be down here or something, depending on how you're adding these up. Okay. Notice that in the rectangle area moment of inertia, go back to this example. Think of this as a skinny rectangle, the cross section. Okay, so think of the cross section as a really skinny rectangle. The moment of inertia is big like this. It doesn't flop down. The moment of inertia is small like this. Just the weight of the paper is plenty to bend it all the way down. And that makes sense with what that formula looks like. The height of that cross section is way more important for determining the size of the area moment of inertia than the width is. So like in this case, it has a really big width. That just doesn't help that much. Its liability is that the h that's getting cubed is tiny, and it's the opposite here. It doesn't have much width, but the width relatively doesn't matter. Yeah. Okay. Now, you can add the area moment of inertias area moments of inertia. For multiple shapes to get the, I sub A for compound shapes, I'll call them. I'll do some examples of this, not today. But before you can add them, you have to calculate those. So like these component shape moments of inertia must be about the same axis. And so how do you get the area moment of inertia of these component shapes to all be about the same axis? So for example, let's say that the cross section looks like this. Okay. Well, the neutral axis of this thing, where would the centroid be? Down here somewhere. Okay. So the neutral axis would be here. That's where our coordinate system would be. Z, Y. And so if we break this up into two pieces, like let's call this rectangle 1 and call this one rectangle 2. And this line here is the neutral axis. Area moment of inertia about the neutral axis is the area moment of inertia of 1 about the neutral axis plus the area moment of inertia of 2 about the neutral axis. And we'll use the parallel axis theorem to calculate the area moment of inertia of 1 about that neutral axis and the area moment of inertia of 2 about the neutral axis. It's the same idea as for mass moments of inertia in dynamics. And the way it works is so the parallel axis theorem says for any shape, the area moment of inertia about some axis A, that can be whatever axis you want to calculate it for, is equal to the area moment of inertia about the shape's neutral axis plus a b squared where d is the distance from what to what, do you think? Yep, from the neutral axis to this new axis. Okay, so notice that formula looks almost identical to the mass moment of inertia formula, and it's the same idea. You have that distance squared. In this case, it's an area moment of inertia, so you multiply it by an area instead of a mass, but same idea. And notice that that also says that for an individual component shape, the smallest area moment of inertia it can have is at its own neutral axis. If you're moving that axis somewhere else, it's going to increase the area moment of inertia of that shape. Okay, so next time, I'll calculate the area moment of inertia for an I-beam. Okay, so I'm going to do that. Let's see, the centroid of an I-beam is here. We know that because it has two lines of symmetry. This is the neutral axis. And so we're going to calculate this by calculating the area moment of inertia of this, this, and this. And then for each one of those, using the parallel axis theorem to figure out what the moment of inertia is for this about this axis. This one will already be about this axis because that's the centroid of that inside rectangle and the centroid of the whole shape. And then this one, parallel axis theorem, will let us calculate about this axis. Okay, and then once we're comfortable with that, then finally we're going on to the formula that lets us calculate the stresses due to bending moments. Okay, done.